So our notes for today are starting with our non-linear functions. Up until this point, the only kind of function you guys have done is your linear function. So now we are doing non-linear functions, which is pretty simple to understand. Those are your functions that do not form a straight line. That's our non-linear function. So everything else that we're going to be doing. So the ones we're doing today are our absolute value graphs. Now, first off, do you guys remember what it means to have absolute value? Anybody remember the definition, man? It has to be a positive number, but why? Absolute value is your distance from zero. So when you're talking about distance from zero, it doesn't matter if you're positive or negative. The positive and negative tells you which direction you're going to go. Positive means you go to the right, negative means you go to the left. But when we're talking absolute value, all we care about is what is your distance from zero. So the distance from zero for a 3 and a negative 3 is going to be the same exact thing. So what ends up happening is it creates a pattern in your table when you get your absolute value. And we'll see what some of those graphs look like in a second. So using your graphing calculator, you want a minimum of 7 points when you're going to graph your absolute value. Our lines, all you needed were 3. Absolute value, you need a minimum of 7. And then I got in here the buttons you push to get to your absolute value. So let's follow that. First thing we're going to do is you're going to go to your y equals, so push your y equals. If you have anything in there, go ahead and clear that out. If you're using one of my calculators, you may have something in there. So to get the absolute value, you're going to push the math button, which is the third one down on the left. You're going to hit the right arrow over once so that NUM is highlighted in the top of your screen. And then that first choice right there, ABS, that is your absolute value. So we'll hit enter. So if you have one of the newer operating systems, it will give you the absolute value bars just like it has up here on my calculator. If you have one of the older systems, yours is going to have ABS and then a parenthesis. So that just means it's the same thing as the absolute values. They're not just going to give you the bars. So we're going to graph first the absolute value of x. So we'll put an x in there and then arrow over once to the right so you're out of the absolute value bars. If you have one of the older calculators, you have to close your parenthesis afterwards so that it says ABS parenthesis x and then close your parenthesis. So let's take a look at the graph of it. Push the graph button. And your graph should take the shape of a V. Because as I was saying, the distance from 0 for a 1 and a negative 1 is exactly the same. Your distance from 2 and negative 2 is exactly the same. So it creates that V pattern to it. So when we're going to graph it, you have to have a table of values to get your 7 points. So when we get our table of values, we hit second and graph, and remember that shows us our table. But you need to find your pattern in your Y column here, your second column. So if you arrow up to the top just a little bit, and if you stop at negative 3 when it's up there, you'll have your pattern. My top number and my bottom number are exactly the same. My next two numbers are the same, then my next two, and I have one number right there in the middle. That is your pattern you want to look for in your absolute value graphs. So once you have that, you can go ahead and copy that down onto your table. Yep. Because yours just has a bigger screen. So you can keep going till you find your pattern in the top and the bottom, but remember you only need 7 points, so you're not going to need the whole screen. So now this column in the middle of my table there, that's for if you don't have a graphing calculator and you have to do it out by hand. You would pick some x values and then in the middle you would be calculating what is the absolute value of negative 3. Well, that's positive 3. What is the absolute value of negative 2? That's 2. Absolute value of negative 1. But if you have a calculator, a graphing calculator, you don't need to use that middle part. So that's just there if you don't have one. So once you have your points on your table, You can go ahead and plot them. So -3, +3. I'm going to put my first point. -2, +2. -1, 1, 0, 0. So you got to draw some nice straight lines with arrows on each ends. So once you have that drawn in there, the f of x equals the absolute value of x. That has a special name to it, and I have it written right up here. That's what we call the parent function. All these different functions we're going to talk about is they have parent functions. What that means is it's the most basic form of the function. So what happens is you have your parent function, and then it can take the parent function and it can move it all about the table. It can move it up, it can move it down, it can make it wider, it can make it more narrow, it can flip it upside down. But the plain old absolute value of x, that's our parent, that's the most basic form of it, and then we move everything from there. So let's try in our calculators. This next one, we're going to do 2 times the absolute value of x. We'll go in our calculators, we go back to our y equals, clear that out. Put your 2 in first, and then do your math. Arrow to the right once to get your absolute value. And then type in your x. So 2 absolute value of x.
Wait a minute. I'm so confused.
So once you have that in there, we can look at the graph. It is the same shape as our first one, as I told you it would be. I mean, it's always going to be the same shape as your parent function. Look at your table again. You want to find your pattern, which this pattern happens to be in the same place where x is -3 up to +3. You got your 6, 6, 4, 4, 2, 2, and then your 0. So that's what you want to copy down on your table in your notes. So when you plot your points, you get your graph on there. What happened to our graph this time? It got more narrow, got narrower. Reason being, because we multiplied it times that 2 out in front. If you multiply it times a number greater than 1, the graph becomes more narrow. So if I multiplied it times 3, times 10, times 11, any number greater than 1, the graph becomes more narrow every single time. Do we have any predictions as to what will happen when I multiply it times 1/2?
It's going to get smaller again.
It's going to get wider. So let's take a look. Go to our y equals. We'll get our fraction in there, 1/2. And then your absolute value of x. You push. So we were right. Multiplying it times 1/2 did make our graph more wider. So anytime you multiply times a fraction like 1/2, 1/3, 1/4, your graph is going to become wider. So our absolute value graphs all have a V shape to it. I always remember it's a V shape because it's absolute value. Value begins with a V, which is the same shape as your graph. The graph of 2 times the absolute value x is narrower than our original parent function, just the absolute value of x. And 1/2 times the absolute value of x is wider than the absolute value of x. So the domain of all 3 graphs. All 3 of them have arrows on the ends, both ends. So what is our domain? X X is an element of the reals. The domain for all three of those is that. Because all three of them, arrows on both ends. Our range for all three of them would not be the same thing. Can it be negative ever? No. So what would our range be? Y is greater than or equal to 0, because they all reach 0, and then they're everything higher than it, so it's everything greater than 0. All right. So in your calculator, I want you to type in quickly negative absolute value of x, and we're just going to sketch the graph, so we don't need to get a table for that. So under your y equals, you're typing in negative absolute value of x. So again, a sketch does not have to be 100% accurate. It is just a sketch. So when we put that negative sign out in front, what happens to our graph? It opens downward. So it makes it flip, or the word we like to use in math language is it reflects it over your x-axis. And it still has the same shape as our original parent function, absolute value of x, with the vertex is still at the origin. Because the coefficient here is a -1, remember they don't always write that 1 when it's a coefficient, but it's there. The graph is an inverted V. So the way that they write this sometimes is they would write that g of x equals negative absolute value of x, g of x being, well, here, let me change that. I used a up there, so I'll change that to a. A of x is the negative of our original function, the absolute value of x. Or sometimes they would write it as your negative a value out in front. A value is always out in front. We were playing with the a value on that first page. We made it a 2, made the graph become more narrow. We made it a 1/2, that made the graph become wider. You make it negative, it makes the graph flip and go upside down. All right, some review of increasing, decreasing. So if we start on the left side of the graph and I follow it, what is it doing first? It's increasing, right? First part of the graph is increasing. It increases until what x value? These x values are what of 0? So x is less than 0 is when that graph is increasing. You break it, you buy it. It's decreasing when x is what than 0? When x is greater than 0, it's decreasing. End behaviors, those ones are easy. Left side is pointing down, right side is pointing down. When is this graph negative?
Right now.
Like the whole thing's negative, right? Except for one spot. I didn't get into this just yet last time because I was just trying to get you to understand the whole positive, negative. Are you positive or negative at 0? No. So when is this function negative? The whole thing is negative, so x is an element of the reals, comma, except x cannot equal 0. So that's just saying everything is negative except for that one point in time when x is 0, because then it's 0 and that's neutral. All right, the word translation. You've heard that word before. What does a translation mean we're doing? The equation will move or slide around the graph. So as I was saying, we can move it up, down. We can move it left, right. We can do a combo up and left, down and right. Doesn't matter. So I have graphed on here already for us our parent function. F of x equals the absolute value of x. What we're going to graph now is this one, absolute value of x plus 1. So let's go to our calculator. Go to our y equals. Get our absolute value of x. And then outside of the absolute value bars, we're going to hit our plus 1. just like it has on our paper. Okay. So what did it do to our graph? It moved it up 1. But we still need our table. When we move it just up, is our table going to change really? No, it still goes -3 to +3. It's just this time it's 4, 3, 2, 1, 2, 3, 4. I'm going to label that graph just as b of x. We don't have to write the full equation. We can write just the function part of it, b of x. Yeah, so this one, instead of +1, this one has -2. So it will move down 2 units. So sometimes if you can figure that out, if you can figure out the transformation that's happening, you don't always have to copy a table of values. I can just take my regular parent function, my f of x, and I can take each point and move them down 2 units. So I move this point down 2. Move this point down 2. That one down 2. And I'll label that graph as c of x. So again, if you're not going to use the table, you're just going to, go with the whole transformation things. You just have to write down what are the transformations that are happening. This one's moving down 2 units. That's my work shown. A little bit? That's good. Now, while some people are still drawing their absolute values, I have some people tell me that c of x is larger than the other ones. But is it really any larger? No. What makes them think it looks larger?
It's moved down, more spread out.
It's more spread out, and the lines here on the sides look longer, so they tell me, oh, it's larger. It's not larger. It's the same exact size. It's just you moved it down the graph so you have more space to continue on those lines. So the graphs are still the same shape, but they have different y-intercepts this time. Our original parent function had a y-intercept at 0. When we had absolute value of x plus 1, it shifted up 1 unit. And then absolute value of x minus 2 shifted down 2 units. So the conclusion, the graph moves up and down according to the value outside of your absolute value. The way we usually write that in function notation, we know our a value, which was out in front. That makes it wider, narrower, can flip it upside down. But then you would have plus c, where sometimes c could be negative, and that's when the graph moves down. C could be positive, that's when our graph moves up. So any value on the outside of there. Sometimes, again, they may write it as, they'll give you a new function name, and they'll say to take the other function plus c, or minus a number. That again is telling you to move your function up or down. If it's outside, it's up or down. So then our next one here is moving it left and right. So again, I already drew our parent function on there for us. F of x equals the absolute value of x. In your calculator, I want you to come up with d of x equals absolute value of x plus 2. You've got to draw your own table this time. I didn't put your table down for you. So the plus 2 is inside of our absolute value bars. So absolute value of x plus 2. So if we look at our graph, which way did it move? move to the left, which is always the opposite of what people think. You would think plus 2 moves it to the right. But being an absolute value, it kind of changes things around a little bit. So this time when we go to get our table, we actually have to move it around a little bit. This time our x values in our table is going to go from -5 to +1. So once you have your table, go ahead and draw your points. So if the absolute value of x plus 2 moved to the left, which way do you think absolute value of x minus 3 would move? To the right. This is going to move it 3 units to the right. Again, if you can identify what the transformation is, write it down, and then go ahead and plot your points that way, where I'm going to take my parent function and move every point 3 units to the right. So absolute value of x plus 2, that was shifted left 2 units. Absolute value of x minus 3 was shifted right 3 units. When you're in the absolute value bars, it's always going to be the opposite of what you think. So conclusion, graph moves left or right opposite the sign inside the absolute value. So in our function notation, that would be a absolute value of x minus b plus your c. It's x minus b in there because, again, it makes you change the sign when you move. Or in our other function notation, if they want you to move left or right, they would actually put it in the parentheses with your x there. So I want you to take a couple minutes, try those 3 problems on that next page. That's kind of like your classwork for today. So what we have to keep in mind, left is inside the absolute value. So I'm going to write f of x equals absolute value of x plus 1, because left is inside, and that's going to be the opposite of what I think. To move left, I got to add. And then my up is on the outside, so plus 3. When you're outside absolute value, everything acts normal. So the next one, they're telling you you're going right 4 units, down 2 units. So you should be having y equal. So, nope, because they started with y this time. I know, they go interchangeably through those. So, right 4 units, how would I write that? Minus 4, and then down 2. So in your last one, they want to know when absolute value of x and y equals 3 intersect. How many times? So this is our parent function. Absolute value of x is just our normal v. Y equals 3 is what kind of a line? Horizontal line up here. So how many times do they cross? 2.